So, Mustafa, and Jamie, I'm Mustafa. We did our project on Spintronics. I did the main topic, he did the subtopics, and this is for computer architecture for Du Young Park. So, for Spintronics, it's no doubt that the world has digitally oriented itself proportionally to the appearance and rise of the power of technology. A lot of the technological fields have been greatly explored and exploited by researchers with the hope of making human life more comfortable than ever before. Alongside these involvements of research into many fields, there has involved an era of digital proficiency that this is the reason as to why some researchers have been diverted into spintronics, commonly known as magno-electronical or spin electronics. Yeah. So, which is a technological advancement exploiting the electron's magnetic moments and its spin rather than its charge. In other words, spintronics spintronics is the study of how the electron of an atom, and more particularly the nuclear, plays a role in the solid state physics, and how devices exploit their spinning properties beside their freedom of degree of charge. Um, so the SSP oriented research has proved of to be one of the STEM factors that have aroused more hunger towards research, particularly exploiting and exploring research at binary levels. For instance, more interests of research have been initiated to explore more about both spin, transportation, and relaxation in either semiconductors or metals, not just because of the prototype significance or potential these areas have demonstrated to the posterity of electronic technology, but also for the projected SSP's technological dominance in the near future, especially in the field of electronics. The fundamental idea on through which these technology works is based on the spin of the electron, in that when an electron is subjected through magnetic fields, its polarization spin automatically acquires a stable condition that can be phenomenal in encoding O's and ones logic bits. Notably, spintronics greatly involves this idea of spin-based computing, through which some electronic logic gates, such as Boolean, are created when the electron spins interact with each other. This provides the basis of spin-based quantum computing, which is um, well known as a magnetic quantum cellular automata (MQCA), hence highlighting the logic tie between the spintronics and the nanomagnetic logic. Um, with the rise of technological dominance in almost every field of study, the discovery of devices such as spin torque transfer, as well as the magnetic tunnel junctions in the 1970s, provided a new research dimension, particularly in the field of spintronics. In such cases, the creation of MTJ occurs when any two or more active conducting electrodes, particularly material that are ferromagnetic, are separated from each other by a thin layer. I think oh yeah. So it's the creation of MTJ occurs when any two or more active conducting electrodes, particularly materials that are separated from each other by a thin layer, that is dielectric, through which electrons can pass through, hence creating electrical conduction. You can see it right here. Well, notably, recent research about these two devices, STT and MTJ, have substantially heightened the significance of these devices in the sense that they are advantageously setting a new technological dimension as they have the potential of replacing the current com- complementary metal oxide semiconductor technology within two integrated circuits that are spin based, such as magnetic random access memories or even spin transistors. Basically, the MTJs contributes a great deal towards the realization of spintronics in the sense that each layer of the electrode either acts as a reference layer or a layer for storage of electricity. Um, for instance, the electric current which tunnels between these layers normally consists of two partial currents specified by either a spin down electron or a spin up electron. The reason why MTJs are of relevance in spintronics is that of their high resistance capabilities, especially at room temperature. This property has enabled them to be of novel significance in modern applicational fields such as that read heads. Yeah, hard drives and even MRAMs. This is because MTJs are scientifically easy to be integrated with CMOS appliances, and for fact they demand a low power access of data means that they are very suitable in spintronics. In other words, it's convenient for one to argue that MTJs provide the face of the future spintronics for either memory or ultra low power computing logic. So, with the studies going around in spintronics rising proportionally with technology, it's not questionable that there are more lucid advantages of MTJs and STTs introductory into the appliances of novel spintronics. This means that some questions are pertaining the combination of semiconductors and other relevant materials uh, such as MTJs still remain open for near future production of spintronic technology. Therefore, there is more need for spintronic research explorations, in particular to create spin polarization through either magnetic or optical injunctions to exploit spin realization in both semiconductors and metals or devices that are spin-based such as amplifiers and p-n junctions, as well as spin-based quantum computation and entanglement of an electron, especially in semiconductors or CMOS, in order to make the study of spintronics bear more fruit in the near term and long term electronic technology. That's it.
Today we will be discussing two topics in spintronics. These two topics are semiconductors and magnetics. Before we do that though, a little recap on spintronics. Spintronics is an emerging field of nanoscale electronics involving the detection and manipulation of electron spins. Electron spins can be detected as a magnetic field having one of two orientations, known as down and up. Spintronic technology has been tested in mass storage components such as hard drives. The technology also holds promise for digital electronics in general. It will give higher data transfer speed, greater processing power, and increased storage capacity, provided the properties of electron spins can be sufficiently controlled for practical applications. What are semiconductors? Semiconductors are materials which have a conductivity between conductors, generally metals, and non-conductors or insulators, such as most ceramics. Semiconductors can be pure elements, such as silicon, or compounds, such as aluminum nitride. Semiconductors are currently used to make devices like phones and watches smaller, faster, and more reliable. Current efforts in designing and manufacturing spintronic devices involve two different approaches. The first is perfecting the existing giant magnetoresistive GMR based technology by either developing new materials with larger spin polarization of electrons or making improvements or variations in the existing devices that allow for better spin filtering. The second effort, which is more radical, focuses on finding novel ways of both generation and utilization of spin polarized currents. These include investigation of spin transport in semiconductors and looking for ways in which semiconductors can function as spin polarizers and spin bulbs. The importance of this effort lies in the fact that the existing metal-based devices do not amplify signals, although they are successful switches or valves, whereas semiconductor-based spintronic devices could, in principle, provide amplification and serve in general as multifunctional devices. The possibility of changing physical properties with an applied electrical field is the feature of semiconducting materials. Diluted magnetic semiconductors, DMS, are used to act as a semiconductor in the absence of an external electrical field. A feature of the DMS is giant spin splitting, which increases the spin polarization of the carriers, usually present in small numbers. Since the beginning of spintronics, there have been attempts to use this property of DMS to build spintronic elements. What are magnetics? We use magnetic fields in conjunction with electrical currents, light, and microwaves in order to control the spin of electrons. It would be significantly more troublesome to harness the spin of the electron without the use of magnetics. Ferromagnetism is the basic mechanism by which certain materials, such as iron, form permanent magnets. Ferromagnetic metals are used as spintronic materials to affect the spins they display. The most practical applications are the giant magnetoresistance and tunneling magnetoresistance. The resistance of layered structures depends on the mutual orientations of magnetization in the neighboring layers. Such elements are already commonly applied as reader heads for magnetic memories. The weak point of the ferromagnetic metals is that it's hard to modify their properties with an applied electrical field. When two ferromagnetic layers are separated by an insulator thin layer, electrical resistance of the multilayer in the perpendicular direction to the film changes depending on the orientations of the magnetizations of ferromagnetic thin layers because of spin-dependent electron tunneling between the two ferromagnetic layers. When the directions of the magnetizations of the two ferromagnetic electrodes are the same, the possibility of electron tunneling between the two ferromagnetic electrodes through the insulator layer become larger, resulting in a larger tunneling current. That's about it.